All right, so this is just a little walkthrough about the convolution of two functions and then how it leads to Laplace transforms. So just a little introduction here. The convolution of two functions, f of t and g of t, is defined by an integral. And it's an integral of f of the first function with respect to w times g of t minus w dw. Did I say f of the first function? I just meant the first function at w. So basically, if you look at f of t, f of w, f, and changing the letter, or changing the function g, so it's basically the integral of f of one function of w, one function of t minus w, integrate from 0 to t. And the reason why I say that is because the convolution is commutative. That might be intuitive, but we'll prove it anyway. Meaning that f star g, that's the notation we use for the convolution, that's right here, is equal to g star f. So we start off with f star g, by definition, integral from 0 to t, f of w, g of t minus w dw. So I'm going to make a substitution. It's going to turn this into a single variable. So I'm going to use the letter u. So over here, I have let u equal t minus w, which means du is equal to negative dw. Remember, it's a dw integral, so that means all of my derivatives are going to be with respect to w. And what that also means is, so I now can replace the t minus w with a u, but the w has to get replaced as well, because once I make a substitution, I don't want w's in my integral anymore. So that means I solve for w, and I get w equals t minus u, and that's what happened here. So putting all of that together, f of w becomes f of t minus u, g of t minus w becomes g of u, the negative from this du equals negative dw goes in there, and then of course, since it's a definite integral, we replace the limits. So when w is equal to 0, substituting into the substitution, u is equal to t, and when w is equal to t, u is equal to 0. So we have this as our next integral, okay? Now, I know that the integral from one limit to the other of a negative means if I take away the negative, I can switch the limits of integration. So that means we are here, and that is exactly the convolution integral, but with f second and g first, because multiplication is commutative, and there we have it. So that's going to be very useful when we go into finding convolutions and then eventually finding transforms and inverse transforms with convolution, because as you can see, one expression is a little bit more complicated than the other. So just to illustrate what's happening here, convolution theorem. Now, I'll prove this in another video, so stay tuned for that. Let's move this up here a little bit. But it basically says if you take the Laplace transform of a convolution, you get the product of the individual transforms. This is big. This is like the product rule for Laplace transforms. You want to end up with the product of two transforms. The function that it came from is the convolution of the functions rather than just the product of the functions. So just to illustrate what's happening, let's say f of t is t to the third, and let's say g of t is t squared. So since we need to know the individual transforms are, as you see, 6 over s to the fourth and 2 over s to the third. So then the convolution is, so here's your f of w, and here's your g of t minus w. This just lists the steps we're crunching through. I know you're able to do this. If you want to pause the video and see if you get the result, I'm just going to kind of walk through, expand the power, multiply through, take the antiderivative with respect to w. In fact, one thing that you might find handy when you're dealing with multiple variables is say that it's w equals t and w equals 0, so you don't accidentally plug in for the wrong variable. And then plug in all your t's and g, or plug in all your w's and g. This step right here is curious because now everything's a t to the sixth. So we combine everything into one fraction, and we get 1 over 60 t to the sixth. And when you know, the Laplace transform of 1 over 60 t to the sixth is 1 over 60 times 6 factorial over s to the seventh, which is 12 over s to the seventh, which just so happens to be the product of the two transforms. Remember, this was the Laplace transform of t to the third, and this was the Laplace transform of t, whoops, this should be third here, of t squared. And as you notice, when you multiply them together, you get 12 over s to the seventh. So if you want to see a more in-depth proof of the convolution theorem for the Laplace transforms, please feel free to view. If not, more videos coming about finding inverses of transforms that are products of each other. Quite fun and will require an integral. Thanks for watching.